All right, this video is going to walk you through what you're looking at when you look at a theorem and how to go about constructing the proof to prove that a sentence is a theorem. So first of all, don't get thrown off by how they look. In our system, a theorem is going to look like a sentence after the therefore slash. And one of the things to notice is that there aren't going to be any premises. The left side of the slash, in other words, is going to be blank. This is because of what a theorem is. So a theorem is the proof system term for a logical truth, which from truth tables you'll remember we call tautologies. Logical truths are sentences that are true no matter what. Again, think about the truth table test for tautologies, that a tautologous sentence is going to be one that's T's all the way down the main connective column. In the proof system, the analog for that is a sentence that can be proven from no premises. Now, for a deeper dive for why that's so, make sure to review chapter 8i, but the short version is that since logical truths are true regardless, or period, or full stop, they don't depend on any premises. In effect, that's the idea of a zero premise proof, is that we can derive some sentences, specifically those that are theorems, from no starting premises. So naturally the question is, well, wait a minute, if we don't have any premises, how do we start the proof? After all, by definition, every line of a proof has to either be a premise or a derived line from earlier steps according to the rules of inference. And we don't have any premises here. Here's the thing, there's actually one way and only one way to start a proof of a theorem, and that is with an assumption for conditional proof or an assumption for indirect proof. That is to say, you are going to be starting indented inside of a subproof. The proof will actually proceed normally, and then at whatever last line is that you're ready to close the proof and actually use CP or IP, citing the whole proof, right? You will unindent. So all of your proofs of theorems will start indented, and then you're done whenever you can use CP or IP and actually have the sentence that you're looking for. And of course, just to clarify, it may be that there are additional lines because we've seen this before in other proofs. Maybe you use CP in the penultimate line, and then perhaps use implication to actually derive your desired conclusion or whatnot. But the point is, for theorems, always start indented in a subproof, which means that you are taking an assumption for CP or for IP, and then you aren't done until you can close that subproof. Now, the next question, of course, is what is that assumption? And that's going to be guided by the normal strategies and tactics for conditional proof and indirect proof. That is to say, for example, if you are proving a theorem whose main operator is a horseshoe, it makes sense to use CP and assume the antecedent as your opening assumption, derive the consequent, and then close the subproof with the use of CP. Here, we don't have a horseshoe. We have looked at a tactic that uses implication and CP to prove disjunctions using CP, but I'm going to bracket that for right now. So instead, we're going to be making an assumption for indirect proof. And that assumption is simply going to be our desired conclusion, but negated. Okay. And if you're handwriting your proofs, this is a place where a drop-down line might make sense because it just reminds you that you are in fact indented. If you're typing this, just go 5 spaces in, 10 spaces in, or whatever, and it'll be obvious that you are indented. Where does the proof go from here? Well, the normal way. Whenever you make an assumption for indirect proof, what you're looking for is a self-contradiction. And how are we going to get one here? Well, actually pretty quickly. After all, De Morgan's actually gets it for us in just the one step. Right? This is a sentence and its negation. And so what happens with indirect proof once we have derived a self-contradiction, well, we close it, so we unindent, and we derive the negation of our initial assumption, citing the entire subproof, and indirect proof. And so this proof, in fact, is an example of what I was talking about before. IP is going to be my penultimate line because, of course, to actually derive the target sentence, I need to use double negation on line 3. Okay. For more interesting and more complicated examples, look at pages 468 to 469, and also, of course, the solution set to all of the 8I exercises. Here I'm going to do another shorter one, but I'm going to demonstrate how to use CP to prove a theorem. So suppose we're trying to prove this sentence as a theorem. And again, the clue that we're proving it as a theorem is that there are no premises. This sentence does have a horseshoe as a main operator, and so that indicates that conditional proof is going to be the easier way to go. So if we are going to make an assumption for conditional proof to begin our proof of this theorem, we just follow the normal tactic for ACP, which is to say we assume the antecedent of the sentence that we want. And as a good practice, maybe make a note of the fact that we want to derive the consequent of the conditional. And what next? Well, again, fall back on our usual strategies and tactics. At this point, it's kind of an old standby strategy, which is, look, B seems to come out of nowhere, right? It's not, you know, this B isn't related, it seems, to the antecedent at all. And so where are we going to get it? Well, most of the time, although not necessarily always, we get random sentence letters by adding them in. And then once we've added in the disjunct B, or some sentence or B, then ideally we've got the negation of that left-hand side, and then we can derive B using DS. Okay, so that ends up being kind of a basic tactic that we've seen before when we've got a sentence that we want that seemingly comes out of left field. How do we know what the left-hand disjunct is going to be, though? Some of you probably already see it, but if you don't, then again, fall back kind of on our usual tactics. We have a conjunction. That's in fact the only sentence that we have so far. So simp out that conjunction. And simp out both sides just to give you some more ingredients to look at. And then now take stock and notice that if, for example, we added, I wrote my notes in too close, I think. Okay. If we added in B onto A, then we do indeed have the ingredients for DS and can derive B. Outside of just trial and error, how would you have known to do this? Well, part of it is just attending to what is actually going on in the sentence and also in the proof. Line 1 is a self-contradiction. And from a theoretical point of view, from a conceptual point of view, anything follows from a self-contradiction. And so we know we are going to be able to derive B. The question is just how. And one way is, given the self-contradiction, one standard way is, in fact, to simply break it apart, add in the new sentence that you want, and then use the denial of that first sentence with the DS pattern. There are also other ways, but this one is probably the most straightforward. How do we finish off this proof? Well, we always have to close our subproofs. That doesn't change from last week. It's just that we never started unindented, but we always have to close over our subproof. We're in a CP strategy, and so how that works is we write over whatever we opened our proof with. In this case, stick parentheses around it because it is a complex compound. Stick a horseshoe after that assumption and copy over whatever the last line of the subproof was. And of course, we cite the entire subproof and rule CP. And we've proven our theorem. We've proven that sentence from 0 premises, which proves that it is a theorem. At the end of the day, proofs of theorems don't change very much at all about your approach to proof construction. Strategies and tactics are actually the same. It's just a little bit of getting used to not seeing premises and remembering that that means that you are always starting with either an assumption for conditional proof or an assumption for indirect proof. As an advanced proof technique, one of the things that theorems give you is just free information. We'll take a look at this in a later video. The basic idea here is that since you can derive theorems from 0 premises, when you are in the proof of any argument whatsoever and you find that a theorem might be useful, you can always insert a proof of a theorem into another proof and derive that sentence for free.